In this chapter we just look at several examples. In example 1 we want to find this shaded area here. Try to solve this task on your own, stop the film now, and here comes the solution. The shaded area is calculated as the difference between the area of the triangle and the area of the sector. The triangle is an isosceles gleichschenkliges triangle, and this altitude h of this triangle corresponds to the radius of the circle. Here we have a right triangle and rechtwinkliges Dreieck. We know this length here, 73, and this is half the base, so 55. So using Pythagoras we can find this altitude and hence also the radius of the circle. hb squared plus h squared here equals mb squared, and solving that for h we get in the end 48, and this is also the radius of the circle. The central angle of the sector is just double this angle alpha, and since we know all the sides in this right triangle, we can calculate alpha using any of the 3 trigonometric functions. So for example, using sine of alpha we get 55 over 73, and hence alpha is the arcsine of 55 divided by 73. And so we find for the shaded area, the area of the triangle 1/2 times AB times H, minus the area of the sector, which is this angle here, so 2 times alpha, 2 times the arcsine 55 divided by 73, divided by 360 degrees times pi r squared. And inserting now all the values, we get in the end 674.1 units squared. The figure here is a sketch of the situation in example 2. We see here the ball, and here we see John's eye, and he looks at the ball with this opening angle. Now try to solve the task, stop the film, and here comes the solution. The 2 lines here are tangents to the circle, and the angle alpha here is just half of the opening angle under which John sees the ball. Since this is a tangent, this radius here is perpendicular to it, senkrecht, and hence we have a right triangle here that we can use to calculate the angle alpha, because this length here, 1 meter or 100 centimeter, is the hypotenuse, and this length here, the 18 centimeter, is the opposite of alpha. And so we get sine of alpha is 18 divided by 100. The opening angle is 2 times alpha, so we get that the opening angle is 2 times arcsine of 18 divided by 100, so approximately 20.7 degrees. How fast are we moving at the kzn due to the rotation of the Earth? This is the question we want to solve in example 3. It is rather difficult, but if you like, you can try it on your own, so stop the film then now, and here comes the solution. Here we see the Earth, we see the axis of the Earth, here we have the kzn, and the kzn is moving on this circle. To find the speed at which the kzn is moving, we need to know a distance that it moves within a certain time. Well, the simplest way to look at it is to say in a full day, in 24 hours, it moves exactly a full circumference of this circle. To find the circumference of this circle, we need this radius r dash. Here the same situation is shown, but just as a cross-section, ein Querschnitt. Let us connect the center of the Earth with the kzn. The length of this line is just the radius of the Earth. And this angle here is by definition the latitude of the kzn. The angle up here is the same like the angle here, since these are alternate angles, Wechselwinkel. And we have a right angle between the axis rotation axis of the Earth and this radius r dash here. So we have a right triangle where we know the hypotenuse, we know one angle, so we can calculate this r dash. So let us start from the beginning. Speed is distance divided by time, so one full turn in 24 hours. So 2 pi r dash divided by 24. Before we can continue, we need to transform the latitude of the coset end, the 47 degrees and 25 minutes, into pure degrees. Well, we have 47 degrees and then the minutes are 25/60ths of a degree, and so we get approximately 47.42 degrees. We now want to find this r dash, the radius of the circle on which the KZN is moving. We see it also here, and here we have this right triangle. We have the hypotenuse, and with respect to this known angle, the r dash is the adjacent, so we need the cosine. And we get cosine of 47.42 degrees is r dash divided by radius of the Earth. We solve this for r dash by multiplying with the radius of the Earth, and we get this expression, and now insert that into the equation for the speed, and we get v equals 2 pi times re times cosine of 47.42 degrees divided by 24, and inserting all the values we get approximately 1128 kilometers per hour, and that's quite impressive because it's actually more than the speed of sound. Solve example 4 on your own, stop the film, and here comes the result. First, Jenny sees the tower under an elevation angle of 20 degrees. Once she's moved 71 meters towards the tower, she sees it under an elevation angle of 30 degrees. Let's call the height of the tower h. Now let us introduce this distance here and call it x. And note that the tower is obviously perpendicular to the floor, so we have a right angle here. Looking at the small triangle here, we have a right triangle, and we can establish now the relationship between h and x using the tangent. Tangent of 30 degrees is h divided by x, and solving for h, we get that h is x times tangent of 30 degrees. Now let's look at the larger right triangle here, and again we can use the tangent of 20 degrees, and we get the tangent of 20 degrees is h opposite divided by x plus 71, the adjacent. Again, we solve this equation for h, so we multiply by x plus 71. We get h is x plus 71 times tangent of 20 degrees. Now, in equation 1 and 2, both times, these expressions here are equal to h, the height of the tower, which means the two of them are equal, so we can set them equal. Let us do that, and then let's expand here the right-hand side. Then let's move all the x's to the left-hand side by subtracting x times tangent 20 degrees. In the next step, we factor out the x on the left-hand side. And at last, we divide by the bracket here, tangent 30 degrees minus tangent 20 degrees. And we get this expression here for x, which is approximately 116.2 meters, but we're not really interested in that because what we're interested in is h, and we find that by inserting this result here into equation 1. So we get for h this expression here, and we find in the end that the tower is approximately 67.1 meters high. Let us now look at the difficult example 5. Ben stands on a cliff 70 meters above a lake. He sees the top of this mountain S opposite of the lake under an elevation angle of 28 degrees. He sees also, when he looks down up to the lake, he sees here the mirrored image of the top of that mountain. So here we have this S dash, and he sees it under an angle of depression beta. The question is, what is the altitude of the top S of that mountain above the lake level? Try to solve this task now on your own. Stop the film, and here comes the solution. We draw here the horizontal line from Ben towards the mountain. Now this point here is 70 meters above the lake level. So this distance here we have here a right triangle with angle alpha, and this distance here is the height h of the top above sea level minus 70 meters. We have a second triangle here, which is also right angled. This distance here is also the height above the sea level, since it is the mirrored image of S, mirrored at the lake level, and this length is then the height plus 70. Let us additionally call this horizontal distance x. Now let us start with the upper triangle here. This is the opposite to alpha, this is the adjacent to alpha, and we get tangent of alpha is h minus 70 divided by x. Solving this for x, we get x equals h minus 70 divided by tangent of alpha. We proceed the same way with the lower triangle. We get that tangent of beta is h plus 70 divided by x, and hence x is h plus 70 divided by tangent beta. Now we can set the two equations 1 and 2 equal, since both are x. H minus 70 divided by tangent alpha equals h plus 70 divided by tangent beta. Multiplying both sides with the common denominator tangent alpha times tangent beta, we get this expression here. Let's expand it and then get all expressions with h on one side here to the left, and those without h on the other side, so plus 70 times tangent beta. In the next step, let's factor out the h on the left hand side, and we can also factor out the 70 on the right hand side, even though we don't have to. We get this equation here, and solving for h, we have to divide by this bracket here, and we get for h the expression 70 times tangent alpha plus tangent beta divided by tangent beta minus tangent alpha. Inserting the values for alpha 28 degrees, for beta 35 degrees in here, we got the approximate height of the top S above the sea level, lake level, is 511.78 meters. Try to solve example 6 on your own. Stop the film, and here comes the solution. Here we have the point P and the center of the circle. Here are the two tangents, and let us now draw the line from P to the center of the circle. Since the angle between the two tangents is 23 degrees, then the angle between the tangent and the horizontal line here is half of the 23 degrees, so 11.5 degrees. Let us now draw the radius to the point where the tangent touches the circle, and we have here a right angle. So we have here a right angled triangle. We know the angle here, 11.5 degrees. This side R here is the opposite of this angle, and this here is the hypotenuse, and the hypotenuse consists of two parts, namely of the 5.2 meters, the distance of the point to the circle line, and the radius R from the circle line to the center of the circle. And so we get sine of the 11.5 degrees is opposite R divided by hypotenuse R plus 5.2. Multiplying both sides by r plus 5.2, we get this equation. Now we expand the left-hand side and then subtract this expression to get all the expressions with r on the right-hand side. Now we factor out the r on the right-hand side and divide by this bracket here and change sides, so we get that r equals to 5.2 times sine of 11.5 degrees divided by 1 minus sine of 11.5 degrees. And we find that the radius is approximately 1.3 meters.